Hello. Hmm.
Sorry, I was muted. Yeah. Can you hear me, Daniel?
Yeah.
Okay, thank you. So okay, I think I have. Um, I didn't choose 1 p.m. because it's ideal. 1 p.m. is probably not the best time lah. Owing to lunch.
Yeah. Sorry about that.
But my afternoon time is very limited lah. Whether holiday or not. That's because uh, to balance between um, helping out with the baby. So we'll take it as a try. Yeah? We'll just try this lot. But
Yeah, I
we
guess
already know that it's not the most ideal place.
just that today I'm not free in the evening. I just realized. That's why I asked you to switch.
Sorry, today you have a prior arrangement, is it?
Yeah. Actually, the arrangement ends at 7:30 plus.
Mhm.
I think it would have been too rushed, lah, which is why I asked to change to now.
Right, right, right. So then today is just let's just take it as a 1 day, a one-off thing lah, and then give it a try, right? Okay. So you have been reading your notes, and I'm expecting question marks, and we'll try our best to explain this lah. Right now, before we go to that, right? Before we go to that, our goal here, I want to define our goals slightly better, right? Because you say that your class experience is your teacher reading from the slides, right?
Yeah.
That didn't change much for the past this 1 year, right? The first year, right? It was like that from the start until the end, correct?
Yeah.
Then let me just confirm something very specific. So he reads the slides for you. He probably tried to explain a little bit what is not on the slide. Maybe something like that. But he doesn't go quickly into questions, examples, or real life situation that they can apply. He does not do that. He does not veer from the slide whatsoever.
Yeah. He doesn't.
I noticed that the slide goes on and on from start until end without much examples. Be it a question, be it a situation, be it whatever. Correct or not?
Yeah.
So that is what happened in the class. There are no discussion on the question until I don't know, until the end. So it seems. Yeah. Right. Okay. So after all this slide is discussed by him, what happened before you guys go to the next topic?
Nothing. We'll just hit on to the next topic. Basically, it was like speed running through the entire syllabus. You saw the contents page that I sent you.
Yeah.
Cover all of that like in the year, which is quite fast. According to the other tuition teacher, he said that like my teacher shouldn't be going this fast, like going at this kind of pace.
He shouldn't. Yep, he shouldn't. He shouldn't at all. Right. I
Because
see.
it doesn't give us enough time to learn stuff properly. Which is understandable, because as soon as like I was still trying to get a grasp of the previous topic, he was already teaching the new one.
Without ever you having a chance to do questions, discuss with him how to apply this, how to apply that, none of that.
He never once went through questions.
He never once ran through questions. You guys don't have a separate session like, okay, we're gonna discuss the concept, slides, la 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 la, and then we're gonna discuss the questions, la 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 la. None of that. None of such. No. Right. So what is the goal of going through all the material? Is there a particular goal that he's trying to achieve here?
Just make us understand.
That's not the way to do it. Okay, right. Okay.
Yeah.
Then I would like, no. I keep assuming that you're gonna go past the holiday, right? Okay, now I'm just gonna assume for a while so that I can, get it out of my system. Usually when my students face a class like that, a class which is not effective for him or her, right? I never said that the teacher was ineffective, but the class was simply ineffective for him or her. I sometimes ask them to do something more effective in class rather than simply paying attention. Because paying attention doesn't seem to work. So let's say, for example, if a student's situation is like you, I'll go through the concept, I'll go through the slides, which is what we're doing right now, right? And then I'm going to ask them to go through a little bit of question, so that when the school comes and your teacher is going through this slide for, 4 to 5 sessions, I'm going to simply ask you to not pay attention. Instead, you're going to do questions regarding this topic in the class. That will be one of the more effective way to simply regain the time loss, right? Something like that. Okay. So I was doing all this stuff with you with that in mind. In case your your class is not effective, then I have in mind you doing questions on class time itself, something like that. Okay.
Okay.
Right. That was the original goal if we go through that. Now, I have to remind myself that is not the case. So therefore, maybe after today, we will jump into the questions already, right? So our goal for these few sessions is for you to have a feel what is the standard of exam, so that you have a better idea what to do afterwards. Okay, right. Okay, so the questions that you have for me, please. Then.
Okay.
Right, I can see them quite clearly, so that's good, right? Unless you want me to see the Jamboard, it is usually I who want you to see the Jamboard, right? I would usually want to see what you have physically, right? Usually that's the case, right?
So the first question is down here. Like, what is a test mass?
Wonderful, right? So he suddenly jumped to potential, right? Like the weird thing, the weird guy. And he's saying that the relationship between work or energy, from now on, I'll correct myself, okay? From now, I'll correct myself. It's not work, it's potential energy. No other explanation yet, but potential energy. So W is now potential energy. So he's saying that in that slide that you're asking, the relationship between potential energy or work with voltage is a mass. I'm ignoring the word test for now, right? Mass times the voltage will be your potential energy, or potential is potential energy divided by mass.
So potential is work done. No.
Potential, right. The change, sorry. Back then you have the topic called work, energy, and power. Work and energy are both dual. You are very tempted to treat them as the same thing. Let me now explain how they are different. Okay, let me explain how they are different. Yeah. Okay. You have a bank account, yes?
Yeah.
you have been saving for some time, right? Do you take it out often? Sometimes use your savings. Do you do that?
Yeah.
All right. So you have an experience of looking your savings go up in general, and you have experience of using your savings sometimes for small things or sometimes for few big things. What's your preference?
Small things.
Right, small things. All right. So here is the explanation. Your bank account is the potential energy. It is basically stored. Potential energy basically means energy stored. In the form of what? We might not be very sure, but it is there, stored, ready to be accessed. Okay. Now, work done. Work done and heat. Work done and heat are two ways to withdraw or put in the savings. So one more time. If in my hand, I should turn on my video. Okay, that's so down. There you go. In my hand, I have a something, right? If I raise this item up, the savings just go up. The savings in the form of potential energy. Can you accept that? This go up. Oh, the savings just went up, right?
Yeah.
Okay, the potential energy just went up. That implies that I make not a withdrawal. That implies that I make a deposit. Look. Okay, that implies that you can see me do the work lah. So there's no need for implying. There's no need for implying. If this is floating and suddenly it goes up, it implies that an invisible entity has done the job. We can be very scared at that point. It still implies somebody doing the job. Make sense? That is the meaning of work. Work is somebody doing the job, therefore making a deposit so that the potential energy goes up. In reality, whether by ghost or by invisible energy or invisible force or by my own hands, the deposit is made. There is no such thing as something go up without a deposit being made. Your savings don't go up without a deposit being made. It may be a ghost depositor, somebody deposit into your account. Who the heck is this guy? It is still deposit is being made. So work done to something is a deposit made, and therefore you will expect the savings to go up. You expect the potential energy to go up. So far, so good?
Yes.
The potential energy goes down. It implies there is a withdrawal made of the same amount. Your savings don't just go down one. Who take it out from your savings? Cannot be like that one. One day your saving is 2,400. The next day is 2,350. You don't see any withdrawal data. That is not okay at all. That doesn't make sense already. Okay. That is what? Sorry.
That's true.
That's true. That means if the potential energy of something goes down, maybe that guy is doing work to somebody else. Him doing work to somebody else implies he has to take certain amount of energy to do the work, hence the withdrawal.
Okay.
Right? So doing work to the object seems like a very weird phrase in physics. It is not. I'm just depositing joules to you. Him doing work, that means he will take out some joule from his own savings. That's all. That's all there is to it. Okay. Heat is just the same way though. Heat is not work. It is still joule. It is still a form of deposit. If I hit you, I'm still giving you energy, which hopefully you will store, hopefully. If you're giving heat to somebody else, instead of doing work to somebody else, it still implies that you're taking energy from your own saving to do the heating. Same thing one. Okay. Now, let's test your understanding a little bit. Kinetic energy depends on the speed. So this guy from steady, no velocity, suddenly it moves. Suddenly it moves. Okay. It can move down, it can move up, it can move left, it can move right. If you suddenly see the object move from steady still what does that imply to the potential energy, to your savings? What does that imply?
Steady, still.
From steady, no velocity, he starts to move.
That means the potential energy decreases.
Because he has taken some energy and converted to kinetic energy or speed.
Okay.
Right. That was the thing that you learned from primary 5 and 6. The whole point of that is to say that you don't just get free energy, you don't just lose energy. It takes energy to do something. If somebody gives some energy to you, your potential energy will automatically go up. That's just natural, naturally happening. Can you? Okay. So now look at back to your question. Back to your question. There is a relationship between potential and potential energy. Potential is almost potential energy. You notice I use that phrase for field. Field is almost force. Potential is almost potential energy. Why bother with potential and field when we have potential energy and force? I promise you that answer will come soon. The test mass is just me saying something like this. The field is almost force, waiting for a mass to pop in. Suddenly we have the force already. The field is waiting for a mass to appear in the field. Then we suddenly have the force. The potential is waiting for the mass to appear. Then suddenly we have the familiar term, potential energy. So, right, though this slide is just talking about the relationship between potential and potential energy, there isn't much to it right now, at least not right now. Okay, so test mass for potential gravity, test charge for potential for electrical potential. That's all.
Okay.
If you're okay with that, next question.
Wait, can you just repeat that one more time? Let's get it.
Right. We are somehow interested more in potential energy and force, probably because we learned them for so long already. Then suddenly these two new guys appear. Potential, which is almost potential energy, and field, which is almost force. Those two guys are very closely related to the two things that we're interested in. So potential energy goes up, implies there's a work done to the mass.
Okay.
That's the implication. So that's why you don't see potential energy here, because work done implies the increase in potential energy. So if there's a work done in moving the test mass, then he implies that maybe the potential energy goes up. That means he implies that there is an increase in potential. That's the implication.
What is test mass? What is
I'm sorry?
Test mass is just a way of saying mass, essentially.
Yes. The mass which is not because remember you have to have two mass and two charge to have the force. Cannot be just one. So the test mass is what you call the other guy. Other guy.
There's a thing that makes the field almost force. Yeah.
No, field is always almost force. Sorry, field is always almost force. There's the thing that makes field become force. There's a thing that makes field become force.
And that is a test mass.
That the other mass. Yeah, two masses. So just now one only have field. Two forces. There's potential energy, just one guy. Or suddenly there's the test mass, the second guy. Sorry, potential. Then potential energy appear when they have two things.
You can say that is M2.
You can say that. You can say that. You can say that there's the other guy. You can say that. Yeah, something like that.
Okay. Okay. Yeah.
If you're happy, let's try the next question.
I'm
going to switch my video off first. And equipotential forces, right? Equipotential forces, your question is what is that, I suppose.
How does it work?
Yeah. Okay, right. Okay, it goes like this. Remember that whenever we try to understand potential, just understand it as almost potential energy. Oh. So equipotential surfaces is almost potential energy.
Yeah.
So potential energy, what you learn from just now is that it depends on height. If I go higher, I have higher potential energy. If I go lower, I have lower potential energy. It is proven by unlocking the potential energy. So if I have an object which is higher, I will unlock its supposed higher potential energy by simply dropping it. I'm unlocking the potential energy, changing it into kinetic energy. The proof comes is that if I fall higher, it's more ouchy than if I fall from a lower height. Simple like that, right? Simple, right? That's a very simple way of proving. See, you have higher potential energy, something like that.
Okay.
I can unlock more, right? Okay, so equipotential is the same, yeah, the surface where the potential is the same. The surface where the potential energy is the same, something like that.
So it's like I say it's like a concept, theoretical.
It's a conceptual, non-physical surface.
Yeah.
And since we're dealing with Earth, which is now round, we are no longer dealing with Earth, which is below us. The Earth below us, frankly speaking, we don't care that it is round. We don't care. We see the sun. Yes, you're saying?
It's not even round. It's like oval.
Slightly. I don't call it oval. We call it like a what do you call it? Oblong or whatever. Yeah, you get the point, right? It's not round. It's slightly squashed, right? But frankly speaking, in our daily life, we don't care.
Okay.
We think that the Earth is that flat thing that we see, right? But conceptually, from a young age, we were told that Earth is round. However, there is no other implication beside that. I don't think we experience the implication besides. I don't know, in our daily life, what is the implication of the Earth is round that we can feel? I have no idea. Time zone difference, maybe. If you travel very far and you jet lag, maybe. Not everybody experience the sun in the same time, so maybe that's the most practical application of Earth being round, right? Of being a sphere. Right? So now come to equipotential surface. We are no longer assuming that the Earth is flat. We are assuming that the Earth is a sphere. Therefore, the equipotential surface, first of all, is also not a flat plane. It is a surface surrounding the Earth because of the similar height. It is now no longer height. It's more like a distance from Earth. So it's a sphere surrounding the Earth. So far, so good?
Yeah.
Right. That is where we say on that sphere is drawn as a circle here. It's actually a sphere. In that sphere, the potential energy are all the same. That I hope makes some sense.
Okay.
So yes,
yeah, I understand. But how does it apply to like voltage?
Oh, very good. A very good application. I will now give you an analogy, okay? I will now give you an analogy which will help you understand why we learn potential. Finally, I can start to explain why do we learn field. We have potential, we have force. Why do we learn potential? We have potential energy. Here's what I'm trying to do, right? To try to give you a value for it. Okay, going to your Jamboard. Now you pay attention to the Jamboard.
Okay.
Page 9, yeah. Now, you're looking at something similar. I'm going to draw something that you should know what, right? You should know what.
Okay.
Right, okay. Something weird, right? Okay. But then you have this thing. Okay. Then maybe something slightly like that. Okay. So, topography from geography, right? You're reading some sort of map, I would say. Right. Now, tell me, what is the thing that you're seeing here? What does it represent?
Mountain.
Good. If this is a mountain, then you will see some numbers, okay? You'll see some numbers, right? You will see that this is 0 meter, right? Okay. You will see that the second line will have an increase in that number. And And you can see that for the sake of our sanity, the unspoken rule is that every contour line, we call this a contour line, right? From geography. Every contour line should experience a constant increase. So 0 to 100, 100 to 200. You don't play things like is first is 0, then the second guy is 125, then the third guy is 200. You don't do such things. You keep it constant so that it makes it easy for people to read. Okay, right? So here is your mountain. It seems that your mountain height is around 400 near the peak. Right? If I ask you to identify where's the peak, where is it?
The center.
Just point. There you go. Now, then I ask you, if you're a seasoned mountaineer, 400 meter very short. So if you're a seasoned mountaineer, let's say I'm going to increase this to 4,000 meter. So now we have a serious mountain in front of us, right? 4 kilometer. That is about, I think that's slightly higher than Kinabalu. I'm not sure, right? Okay. So if you're a seasoned mountaineer, which path will you take? Based on this map.
Probably this.
That's a seasoned mountaineer. Okay, let me ask you. If you're a seasoned mountaineer and you're bringing your friends, which are, it's not even amateur. They haven't climbed mountain for the last.
It will be like, as in he can handle it, so it'll be the shortest route.
And why is that reserved? There's a route reserved for the seasoned mountaineers.
Because it's the steepest.
So hardest, right? But if you're bringing your friends and you care about their safety, you will take which route?
Oh, yes, son.
Yeah, probably even do this, by the way. Probably you'll even do ding, 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 ding. You get my point? That's even slower and maybe more scenic and at the same time easier. You can take that kind of pathway. Can, right? You can.
A lot longer.
Yeah. But maybe for them, it is necessary, no? Maybe. Yeah, you get what I mean. Right? So you and I have a very clear and similar understanding of this map. Right? Now, this contour line, by nature, if we want to make it of some use, to us, the contour line needs to be equi-height. Correct? It is implied that this line is all 100 meter. You don't have to ask. All of that is 100 meter one. The other line, 2,000, sorry, 3,000, 4,000. So it's a contour line. The technical name is equi-height line. Okay, a line of equal height. Except that is the exact same concept as equipotential surface. In the equipotential surface, when you go from one equipotential surface to another one, it's like going from one contour line to another contour line. Right? If you're a seasoned mountaineer, you go from here to here. If you're unseasoned, you will go a little bit of a longer path. Right? The end result is still the same. I reach the height from 0 meter to 1,000 meter if I go from this contour line to this contour line. If I approach it from here to here, the same result. If I approach it from here to here, the same result. I would have increased my potential by doing so. So the important thing about equipotential surface is that you usually travel from one surface to another when you are increasing or decreasing your potential energy. If you're decreasing your potential energy, there's an implication that you have traveled from one surface to the other surface. There's that implication.
Okay.
Right? From one height to another height. Why is this important? In the same way that you would rely on contour lines to plot your path, you will find that useful for equipotential surface also. More on that on the question. Okay, but my promise is very simple. This is not about potential energy, correct or not? It's not. It's about the height. Okay, that's all the information you need. I don't care. You're saying?
You could also represent gravitational potential. If you think about it, it's like 400 was the most.
No, you cannot represent it with a line. No, you can. That doesn't make a lot of sense.
Because if you look at the line, it's all the distance from the.
Wait. Are you talking about force or energy? Sorry. Which one are you talking about? Sorry, Ethan?
Like, as in, like, your analogy also works in the sense that, like, this analogy could also represent, like, in a roundabout manner, the gravitational potential energy. Because at 1,000, this 1,000.
Oh, it does. No, it does. Of
Yeah.
course, it does. Now,
Yeah,
why don't we use potential energy? Why don't? Because your mass and your friend's mass is different one. Your mass is, let's say, I don't know, your mass, you look quite lean built. So your mass is what, 58, I think. Right? You have a friend whose mass is 90.
Yeah.
And he's trying to climb with you. Right? At 4,000 meters, his potential energy will have increased much more than you at 4,000 meters, simply because he's heavier than you. He's more massive than you, right? But for mapping and tracking purpose, we don't care about that. We don't care the fact that you need more energy than me. I acknowledge that you need more energy. You should know you're climbing a mountain with such mass. We should know. I will end up helping you bring your stuff. You will end up struggling climbing it. I have to be ready for that. Potential energy is important. But for the sake of charting the path and the map, I don't care about your mass for a while. I just care about the height.
Okay,
something like that.
I need to change the earphones.
Oh, right.
Others speaking behind. Right.
Okay. Okay, slightly softer.
Hello.
How much? Did you hear my analogy about your friend and
does this work?
Okay lah.
Okay.
It's less crowded though at the back, so I get that.
Okay.
So, did you hear my on your friend and you like, your friend is heavier than you?
Yeah.
Right. So potential energy is important. Yeah. You will expect your friend to be more tired than you. He's carrying 30 more kg than you in his own body, trying to climb the same height. Whatever stuff he end up bringing, you will have to help. Like that. So potential energy matters a lot. But in terms of pathing away or looking at the map, the height is. I don't want the fact that at 4,000 meters, his potential energy is greater than mine. I don't want that to confuse my thing or my map. I don't want that. I want to worry about the height and the path that I'm taking instead of the potential energy increase between me and him. Even though that is also important. My point is height or potential. I'm analyzing height with potential has its uses lah in certain cases lah. Even though potential energy is always the main thing.
Okay.
Right. Okay. So what are the uses in our question? You will see later. But in real life, I'll keep going back to a contour line or a contour map because that's the best analogy. Okay. Any questions so far on the concept of equipotential surface?
Yeah. Wait, I don't think you really understood my question. I was asking about how does it work for charge? Is it like the 40 volt, 30 volt, 20 volt, 10 volt?
Yeah.
Is it like that because it dissipates? Or?
Oh no. So the potential is not caused by the test charge, right? The potential is caused by the charge in the middle, right? Assuming that there's a charge.
Oh,
right?
so these are potential. This is not like actual.
Yeah,
Okay,
that's the the pretend surface, right? The pretend surface, the pretend equipotential surfaces of the charge in the middle. When you put another charge there, you will still have the potential, but you will be dealing with potential energy only.
So they are like, the potential will decrease because of the distance from the point charge.
That makes sense. So let's say you're going from the outer surface, which is, I don't know, what is that? How many volts is that?
It's 40 volts in the center, 30, 20, and 10.
Okay, I go from 10 to 20, right? I have an increase in potential, correct? Right? Now, I'll give you a few details. The test charge, the other charge which just appeared in front of us, can be positive and can be positive and can be negative. The positive charge, one of them, goes and climb from 10 to 20, right? Does that make sense for me to use the word climb for the positive test charge going from 10 to 20? Make sense or not?
Yeah.
How about a negative test charge? The negative test charge climbs from 10 to 20. Does that make sense?
Negative test charge.
Positive climb, negative also climb. Make sense or not?
Yes, so yeah.
No, absolutely not. This equipotential surfaces 10, 20, 30. It implies directly that the charge in the middle is positive. It's a direct implication. I don't have to, he doesn't have to tell me it's clearly positive. Because simply as you go near the center, it's more positive. That's all. Okay, yeah? So another positive charge trying to go from 10 to 20 implies that he's trying to go nearer to the center, nearer to the peak. He will experience a resistive force. Therefore, it is as if he is climbing an invisible mountain. Okay? A negative charge, on the other hand, experiences the total opposite. What do I mean by the total opposite? I mean,
it will increase as it moves away from the point charge.
You will climb, yeah. If you're moving away from the charge, you will feel that you're climbing out of it. So I will illustrate it like this. Right? So look at that. I just copied the picture. I'll try to make it as the same size. Right? So same size, same shape, same thing, except for one big difference. Okay. Oh, don't delete that. Yeah, undo, just undo it. Yeah. Okay, there you go. So you notice that I copied the two pictures. The left side is a mountain. I agree with you. Is the guy on the left side, on the right side, a mountain also?
Valley.
Is a valley or a lake or whatever, like a very deep thing, a very deep trench, right? You will have no problem going to the center of the trench or the lake. You will have trouble going out. Okay. So a positive charge approaching another positive charge is like climbing. A negative charge approaching a positive charge, it's like dropping into a lake. He will not have any problem at all dropping into climbing out.
This is assuming that the center is positive, right?
Yes. In your lecture note, it's not an assumption because it's clearly getting more positive. That's how we know.
So this is the
So a positive approaching another positive is feeling like he's climbing a mountain. It is really the feeling. It is really the feeling. The contour is the same with the negative one, but it is the opposite feeling.
So it's like it gets easier to move in because
go into the center if you are negative. Yeah, you don't have to make effort. By the way, you can't even stop your climb. You cannot even stop your descent. It takes effort to stop your descent, so to speak. If you don't make any effort, you will just descend one. Fair, right?
Yeah, okay. Also, yeah. That's what it means. Okay.
Right. So the equipotential surfaces tells you the shape, right? The shape is simple in your lecture note. It will be more complicated in exam, right? But the point of those surfaces is to tell you whether you're in a mountain situation or in a lake situation. That's usually what's going on most of the time. Yeah. You can have two lakes, by the way. You can have two mountains, by the way. You can. That's totally possible. And that's what usually happens in exam. I will gather. Okay.
Okay. Can you
Okay.
show like one of the questions later or?
Hopefully, because that is the goal. That's the goal. But let's answer your questions first, right?
Sure, sure.
Right. So when you're happy, you move on. All right.
It's a gravitational potential energy.
Right. So gravitational potential energy, the focus is potential energy, right? But this one is gravity one, not the electric one. So right. So they give you the formula. So what exactly is your question here? Sorry.
The highlighted part. It's just like this equation can only be used. The distance is just not very large.
Which formula? He's talking about the formula given there, which is correct. This is the original formula you learned from, I don't know, primer, I think secondary one, I think secondary one or secondary two, I don't know. Right? You know that formula, mgh, man. More appropriately, mg delta h. So he's saying that that formula worked until now. Until now, that formula works. If we pretend that the Earth is not round, that's usually how we pretend. Or if the Earth is round, you don't move too much. When we say we don't move too much, that means in the range of 100 meter to 200 meter, something like that. You can assume that your small g is constant.
Okay.
That's what he's saying.
The question is like, why is that so?
Why, sorry? Why is that, sorry?
I can't really grasp why the distance has to be not very large.
Because your small g depends on something, right? What does your small g depend on? Your small g has a formula. Yesterday, I introduced that to you. Tell me the formula. Don't look for it. Small g is almost force. So what's the force formula? G double M over R squared. Right? So the small g will be big G and then single M over R squared. The varying of the small g depends on the R log, the distance, correct or not? Remember, I say a variable. So the variable is the R. The R changes, the G changes, correct? If I'm not making any sense, I cannot answer your question. Does it make sense? Okay, I want you to write down the formula one more time for small g. Right now, small g is big G 1m over R squared. Now separate the big G and big M with separate it from the 1 over R squared. Right. So you're gonna put 1 over R squared to the slightly to the right. Okay. Good. Now, what changes the small g? Okay. The distance. So if you don't move your distance too much, your small g don't change too much, though. Voila. Correct?
You don't want the g to change because if the g here for this to work, g has to be a constant.
Correct. So how do you keep that assumption correct? By not moving, so to speak, by not changing your distance too much. Make sense, ma?
Yeah.
And I think that's the answer to your question. Did I get the question correct?
Yeah.
Good. Something like that.
So just like a random question. How was like the margin of goals? Like 100 meters, 200 meters?
You got softer as you speak faster.
I just wondering the margin of error. Is it like 100 meters?
Yeah.
You mentioned
100 to 200 meter is probably fine.
So not very large would be.
Let me put it another way. The tallest building in Singapore, I don't know, let's just call it the Marina Bay Sands. I'm sure we can find a higher one, right? But let's say Marina Bay Sands has, each story is around 4 meters. Let's say that. So you go up from the lowest floor, 0, ground floor, up to the highest floor. Let's say that's 200 meters, okay?
Okay.
By right, the G that you experience changes a little bit around the 3SF figure already, around there already. So it's like in the ground level is slightly higher than on top because you are away from the earth, so your G becomes smaller, if that makes sense, right? Okay, so on the ground, let's say it's 9.81 something something, then maybe on the top of MBS, 200 meter above, maybe it's already 9.80 something like that, something like that.
But it's not enough to have like a large effect, but it's just like
It doesn't justify the more complicated formula.
Ah,
Just use your just simplify your life, Physicists are very practical one. If they can get away with it, they will use the simple formula. But they are trying to teach you when you cannot get away from it. Therefore, you have to use the more complicated formula. That's what they're trying to say here.
okay.
They're not trying to confuse you in any way. They're not. They're not trying to emulate the previous learning. They're not. Okay. Yeah. If you are happy with the explanation, let's move on to the next one. If the what is your question? Tell me what's your question.
I need to understand this.
Can you zoom in a little bit? The video gets blurrier, so just zoom in. Okay, nice. Okay. Okay.
Just the potential energy must be negative, which I don't understand.
Now you listen to me. This is important. Just now in page 9 of your Jamboard, pay attention to your Jamboard. We were discussing that there's a possibility of something appearing as a mountain or a lake, depending on who you are, right? If you look at the positive charge and you're a positive charge, that's a mountain. If you're looking at a positive charge and you're a negative charge, are a lake. He's a lake. I'm going to flip the role a little bit. If you are looking at a negative charge and you are negative, you are looking at a mountain.
This might change because maybe the radius is slow.
What do you think?
So that's the way we can.
Yeah, negative charge. Yeah.
You're a negative charge looking at another negative charge.
But on exception, he might
You will be looking at a mountain or lake. Mountain. I agree with you. If you can already imagine that correctly, you're already on a good way, a good path. If you're a negative charge looking at a positive charge, you are looking at
but it is true. Yeah.
a lake. Am I correct?
Okay.
Now, it's very weird. Yeah? Your voice is being drowned by the background voice. I find that very weird. How can your mic be picking up more than you? That doesn't make sense.
So my mother is like talking loud.
Oh, right.
She's on another call. Sorry about that.
Right. Okay. I'll try my best to hear you. Yeah. Okay. So yeah, now let me ask you something. With a mass looking at another mass, there is no positive or negative mass, right? There is no such thing. So far, so good. If you are a mass looking at another mass, that's the only situation possible. Are you looking at a mountain? Are you looking at a lake? Is it possible to switch? What is the situation here? What do you think? What are you looking at as a mass looking at another mass?
A mass looking at another mass.
Are you looking at a mountain, a lake, or don't know, or nothing?
It depends on the scale of the mass.
Okay.
Like, if they're two very big masses, then it would probably be a lake.
So let's say the moon and the moon is looking at the earth. The moon sees lake and experience a lake. Again, what does a lake mean? A lake means no effort needed to go closer. Much effort needed to climb out. Make sense? That's what a lake means. Okay? That's French. The earth look at the sun. The earth see a lake also No effort needed to go closer. Much effort needed to go further. So far, so good. That's what you
What
mean.
does the sun see?
The sun, I mean, you're fair to say that if a mountain is bigger than another mountain, he doesn't care too much lah. To be fair, to be fair lah. So there is that imbalance lah. Like maybe now take us lah. We take us. We can see both the moon and the earth, and even the sun. But if we disappear, if our mass disappear, the moon and the earth won't care too much, right? So we just live with that asymmetry, no? If you look at the moon, you see a lake. If you look at the earth, you see another big lake. That's all, correct?
Yeah.
Is there a possibility of a mass looking at another mass and see a mountain? Is there a possibility or not? Like the earth look at the moon, oh, that's a mountain. Is that possible?
No. I don't
It's a smaller lake lah, a smaller lake than me. That's all lah, right? That's
Yeah.
all. Okay. This is what the slide is talking about. You see the moon. You need no effort to go nearer to the moon, except for the fact that you're too close to Earth already. Your journey to the moon will feel like climbing a mountain, not because of moon. It's because of the lake of Earth you are in. You have to go out of the lake of Earth first. So the center is the Earth, right? The moon is actually here. It feels like you have to climb a mountain. There is no mountain. There is only deeper lake and slightly smaller lake. And you're trying to go out of the deeper lake. That's all. This makes sense?
Yeah.
Right? Now, for the mountain, it's the other way around. Right? If you try to go away from the mountain, it is like you're dropping because you don't have any effort needed to go away from the mountain. It's like a lake, no? There is no effort needed to go away, something like that. Now, back to this slide. He's saying that at infinity, your 0 meter is at infinity. That's what he's saying. Your 0 meter is not at a fixed distance or finite distance. To be fair, the well of Earth extends until infinity. Only at infinity or at 0 meter. You are at the beach. You're trying to climb from the depth of the lake. That's what he's just trying to say. That's all. The lake ends at infinity.
The infinity is 0 thing, I don't really.
Right. So here's the Earth, right?
The 0 of potential energy taken to be at infinity.
Yeah. Like in real life, you can say that this is 0 meter. What's beyond this? Maybe another 0 meter, because maybe this is a flat surface. Maybe lah. At the beach, you see the flat surface of 0 meter lah, so to speak, at the beach, right? Now, but we're talking about Earth and Moon and Asta, trapped in the middle. If you want to get away from Earth, you are getting away from a negative potential energy into a slightly higher potential energy lah, slightly lesser negative lah, right? You're climbing away to coming out. So far, so good.
Yeah.
Because of the formula, because of the physics, the formula represents physics, not reality. 1 over r squared. Only at 1 over infinity does everything become 0. So the lake will not end at infinity. However, to be practical, at a sufficient distance far away, you don't have to care too much already. It becomes very small. Because remember the graph, the graph is like this. The graph is like this. See something like that. It will approach 0, but at a sufficient distance, it's around 0 lah. Around there lah. That's all. That's all it is.
And it's so close to 0, you just assume it's 0.
You have more pressing things to worry about, like the well of another being. For example, the moon. If you get far away from Earth, you will start to worry more about the well of moon or the well of the sun already. The well of Earth doesn't really matter already. Right? You are just jumping between lakes, basically.
Okay.
Right.
Can.
So that's what it means. At infinity, it is 0. Yeah, lah, the lake ends at infinity. That's all.
Okay.
Okay, so far so good. Good question so far. If you would like to move on.
Sorry, can I have like a 1 or 2 minute break? I just need to go fill my water bottle.
I'm sorry, I cannot hear you at all.
Can I get like a 1 or 2 minute break? Because I need to go fill my water bottle.
Yes, please.
Okay.
But he has to check with you now. No, so what he's saying is that Sunan is in charge of stock. Sunan is in charge of stock. So- No. If you want to find out questions about stock, you go and ask GM or Sunan. You're not in charge of stock. You can't do. You don't know what to warehouse. Okay? What he's saying is, don't ask him when stock coming in. When are you putting out the level? He will put out a level when stock comes in. He's not in charge of telling you when the stock is coming in. That's what he's saying. Right? It makes sense, right? 6,000 people asking you can't do it. That's what he's saying. So, like I said, if you have a question and then you think about this question about stock, then you ask someone. The bundle will depend on the stock. That's what, but to me, it's like once the stock is in, will you see? It's very easy.
Hello.
Yes.
Anyway, it's here now, right? It's here now.
If you want to ask another question.
Hello.
Yes, I can hear you.
Do you?
Can you hear me? Sorry, can you hear me?
Yeah.
All right. If you would like to ask another question.
Can you hear me?
I can. Can you hear me?
Okay. Yeah, I can.
Right. Yes. All right. Yes, I can.
Okay. Okay, next question.
Mhm.
Yeah. Sorry.
Infinity, right? So
Yeah.
he say infinity means he's saying the edge of the lake. He's just saying that. We start
it's from
jumping into the
outside the equation.
at the edge of the lake, look, maybe let's say. Where's the edge of the lake? I mean, just to be mathematically correct, is at infinity. To be mathematically correct, right? Right. So let me test you. Let me test you a little bit, because the lake is not. I keep bringing in the lake so that it doesn't become conceptual, right? It becomes more real. Now, this guy is saying that I need to do work if oh no. Right. So it's from infinity to a point, right? So let me put infinity here. There's infinity, there you go, at 0, right? The concept of infinity is not the infinity, it's at 0 meter. That's the point. That's the whole point. Okay? 0 meter.
Okay.
Bringing it to, I don't know, minus 2000 there. Minus 2000 is here. Through this roundabout path, right? The path doesn't matter. You're going from 0 meter to minus 2000 meter. Because if you get closer, you are getting more minus. You're going into the lake. Make sense so far?
Mm-hmm.
Right. Logically, do we need to help him go from 0 to minus 2000 meter?
No.
No, correct. You will just do it quote unquote automatically. So what does it mean by work done? How come there's a work done to the mass, right? So the guy doing the work, the guy that caused everything to be automatic is actually the earth,
The center.
the center
yeah.
guy, the center mass. The center mass is the guy doing the work. He is doing the work of pulling everybody into himself. We
You say
don't
that
have
it's
to do it.
exerting force on the.
Correct. As you have experienced, that's called gravity.
Mhm.
That's called gravity. So the center mass is doing all the work so that the test mass don't have to. We also don't have to.
Okay.
Right. So just to clarify that phrasing, it'll be important later on. Okay.
Okay.
Right. If you're happy, we continue to the
Yeah, this one is the velocity of escape. Right?
right. Okay. So escaping implies you're escaping from a mountain or from a well?
From a valley, a lake. Sorry.
Lake, valley, right? Okay. Why doesn't it make sense to say we're escaping from a mountain?
Because you don't really go into a mountain when you want to escape from something.
Yeah, yeah.
It's
So
like
you just
something
roll down lah.
falling
If you're in a mountain, right? Just roll down,
Yeah.
right? Yeah, that's all lah. Like you will need effort to climb to the mountain lah, right? You will need effort to do that. Right? So you don't call that an escape speed. Now, escape speed implies that you're going out from a lake. It also implies the direction. No? Where is the direction of escape? Just to be clear.
Away from the lake.
Right, away from the lake. Do we start from the middle of the lake or do we start nearer the edge of the lake? Doesn't matter. We are still trying to escape. Okay. So in our context, escape speed usually means escaping from Earth lah, or escaping from moon, or escaping from sun, whatever. Right? Escaping from something very big, not something small. So what? So far so good, yeah? Right. I'm going to pretend that we are just escaping from Earth. So we are close to the center, right? We are not exactly at the center of the Earth. We're just on the surface of the Earth. So close to the center, right? So escaping from Earth implies that you go from minus 4,000 to 0. That is what escape means. If you just go through minus 1,000, that's not escape.
You have to get to 0.
You need to get to 0. Then you
in 0 is
fully escape from
infinity.
it. Correct. That's why it's conceptual. In reality, you just escape far enough lah, so
Yeah,
that
out
the
of the
Earth
reach.
doesn't matter. Yeah, the Earth doesn't matter. Other things are matter more. Like if you escape from Earth far enough, you encounter Mars. Then Mars become a problem, right? But Earth is much less of a problem than Mars. So who cares? But just follow the mathematical concept, no? Like if you are escaping, you escape all the way to infinity. Because why? Because that's where 0 is. That's where the beach are. We don't have to go philosophical, therefore we can never escape. No need to do that. No need to go philosophical.
Wait, will they ask like determine when the what's this thing called again? Wait, when the equipotential line of like Earth
Equipotential
0.
surface lah. Right?
Yeah.
The equipotential surface of Earth reaches 0 at infinity. No? That's all.
They'll okay, then like let's say they give us a number like reaches. Will it be in newtons?
I know the if you want the unit, which is very weird, the unit will be energy over mass. Simple, right? Joule over kilogram.
So when it reaches like let's say X amount of joules per kilogram, let's say like 100.
Minus
it reaches
100. It's always
minus 100. Is there like a formula to determine that? Or?
Of course. The formula you know already. The formula is the formula of the potential of Earth, a potential energy that you're asking for. Potential is big G, and then 1m over 1r. That's all.
Oh yeah, yeah, I remember we went through it
Right.
yesterday.
You have the formula. If they ask you specifically where, that means you're calculating the R. You can just input, you can just input the value, the G value, and the mass of the Earth value. You will get your R. Simple as that.
Is
The VG lah, the VG. GM1/R. Right.
so you're solving for R.
Then you just have to input the mass of Earth. The big G is always there, and the precise number minus 100 something like that you're aiming for.
Ooh.
That's all. That's all. Then you know how far that distance will be. You do know that.
Okay.
So again, escape speed implies that. So why do we say escape speed? Because watch. It's not called escape energy. Whereas in fact, that is the thing you need. You need escape energy because you're climbing up. You will increase your potential energy. That's what it means to escape a lake. You have to increase your potential energy. Make sense so far?
Yeah.
To increase your savings, you have to make deposit, correct? Where does the deposit come from? Where does the deposit come from? It must come from somebody or something else. In this case, the fuel. So the fuel must give you enough chemical energy to make the deposit of potential energy needed. So far, so good? However, the nature of our reality is we cannot just eat fuel and we suddenly go up. We cannot. We have to burn the fuel. So that means from chemical energy, it has to convert to kinetic energy first. The kinetic energy is the one that can be deposited into the potential energy. You're saving. So chemical energy becomes kinetic energy, kinetic becomes potential energy. Okay, so far so good? So
Yeah.
how many kinetic energy do you need for the supposed increase in potential energy?
A lot.
Okay, you're climbing from minus 4,000 meter to 0 meter, correct? That is your increase in height. From there, you can calculate your increase in potential energy, correct?
Yeah, MGH.
MGH. Let's use MGH for now, right? It is no longer applicable here, but let's use MGH for now. So you have your supposed increase in deposit. Okay, let's call that, I don't know, $400,000, right? So how many amount of money do you need in order to make a $400,000 deposit?
400,000.
Precisely. That's the point. The escape kinetic energy is equivalent to whatever potential energy you need to deposit. In order to escape, you must have $400,000 of kinetic energy. Ideally. In reality, you need much more than that. In reality, but ideally, you need at least 400,000. Right? Okay, so there comes the escape speed, because the escape kinetic energy is $400,000. From kinetic energy, you can convert easily to speed. That's all. That's your escape speed. Your escape speed is your theoretical minimum speed needed, which again, in reality, because of losses, you need much more than that.
Okay. Yeah.
Something like that. If you can understand my explanation, even by a little bit, it means you already imagine things as lake or mountain. That's a good direction. That's a good direction.
We kind of get it. Not 100% yet.
So if you know that your escape requires $400,000 and you only have $50,000, should you try to escape?
No.
Correct. Why not?
Because you don't even have to escape.
And if you try, what will happen?
You just fail.
And therefore waste your 50,000. You'll just go back to Earth if you try to escape. You don't go up and stay there. You go up and then you go down, therefore wasting your 50,000.
Mhm.
something
The
like
potential energy in this case is the stored fuel, right?
the what, sorry,
The
no,
fuel.
no, the potential energy you need it depends on your client. You need something to convert to potential energy. I suppose that's the chemical energy, like, I suppose that.
Ah,
And when you convert chemical energy field into kinetic energy first, then kinetic energy to potential, the reality is it's complex. You need so much more chemical energy than just 100,000 because the conversion, a lot of loss,
yeah.
something like that. So in reality, you probably need 1.2 million, something like that, just to escape 400,000.
And
Yeah. So I suppose at the year 69, when people launch man to moon, it is really a big deal. It is really, really, really a big deal. Something like that.
big deal for science.
I suppose. Big money also. But at least it was successful. At least after 20 years, GPS come out of it. Something like that.
Okay.
If you're happy with that, on to the next question.
There's one more at the bottom. So
Mhm.
just note that V escape does not depend on the mass of the rocket. But that fundamentally doesn't make sense to me, because wouldn't the weight of the mass of the rocket be like the number one hindrance in the escape of the rocket? Like the heavier it is, the harder it is for it to leave. So why does it not affect the velocity?
You are thinking about kinetic energy. The kinetic energy depends. The potential energy. The potential energy increases when you're heavier. When you're a heavy person trying to climb a mountain, you need more potential energy than the lighter friend next to you. Correct? If you carry more things in your bag, even though you are a lighter person, you're bringing more mass. Therefore, you need more potential energy to climb the mountain. You are thinking about potential energy, and that is always true. I agree with you. He's talking about the speed. So he goes like this. For a heavier person to reach the same speed as you, a lighter person, he needs to exert more force, or he needs to spend more. Same thing, like, correct? Therefore, it means the speed of escape does not depend on the mass. Yeah, but to reach that speed, you need to exert more force or more energy. So still go back to your logic. I won't explain why the speed doesn't depend on the mass, but I have explained to you that it is harder to reach that speed if you're heavier. That is always true. So rockets are made lighter. Rockets are made very light. As light as possible. It's an aluminum can full of fuel. Really, really. It's all fuel.
Yeah.
Have you watched? Maybe you haven't. Maybe you didn't. You probably did. Did you watch the movie The Martian?
Yeah.
Then you know the scene where they take off everything from the rocket. What?
Yeah.
Remember, he talked to you, and then, oh wait, you have to take off everything. Your chairs are more.
Oh yeah.
Your chairs are more. And then he messaged back. Remember the message take 20 minutes to arrive from Mars, right? Remember they're doing long distance, really long distance texting. 20 minutes. He basically replied, what the, something like that. Yeah, but he has to do that so that he can escape from Mars to the waiting friends. He's trying to escape.
Yeah.
If you're lighter, you escape at this speed. If you're heavier, you escape at this speed also. However, you take much more fuel.
So the speed is a speed that doesn't change.
As long as you hit that speed, you are escaping. So hit that speed with as little mass as possible.
Opposite of terminal velocity, you say.
I suppose. Yeah.
In a way, in a weird way.
In a way, you are not, because terminal velocity implies that you're dropping to something. Implies that. Whereas escape velocity implies that you're trying to get away from a lake. Usually you're dropping to a lake or you're getting away from a lake. the fact that terminal velocity is the same for everybody is a totally different mechanism than what we're talking about here. Just say.
Yeah, I know. It's like the
Yeah.
that's why I say in a weird way, lah. It's not
Yeah,
technically
yeah.
correct.
Yeah, they are only superficially the same, but they are not.
Yeah.
So next time you see this and you imagine the Martian scene, remember that in order to reach that critical speed, he takes off everything he could. So in a practical way, reaching the V escape depends on the mass of the rocket. It does. Reaching the speed depends. The lighter the mass, the easier it is. Maybe that's what you want to write, like, so that you don't, because what you're thinking is not wrong. What you're thinking is not wrong.
Different amount of energy, right?
To reach the escape speed requires more energy.
But the V escape
It's the same for everybody. It's the same for everybody. The goal is the same for everybody. Like the mountain is 4,000 meters. You climb 4,000. I climb 4,000. But if I carry too much, I need more effort. It's still 4,000.
So for Earth, it's about 11 kilometers per second.
I guess it is that fast, no? I guess. That's crazy, by the way. That's crazy.
Yeah.
Crazy. That means you can get to your school in 1/3 of a second. I don't know, half of a second, maybe something like that. I don't know.
It's like teleportation already.
Yep.
Okay.
You have,
I only have a few more questions.
Good. We only have 10 minutes.
I didn't go all the way.
No problem. So really no problem. Because you're still forming your understanding. You might have enough to try a question. No, you might have enough understanding for that. Okay. So still ask next one. This one is it. Gravitational field strength is not the same as negative potential gradient. Right. Okay. So we talk about the relationship.
It is the same.
I'm sorry, it is the same, right? So remember, I was talking about differentiation.
Yeah.
Do you still remember what's the relationship between back then I say work, so potential energy and force, which is the same relationship as a potential and field. What's the relationship?
And you differentiate potential energy, you get force.
And when you differentiate potential, you get
field.
Yeah. So now in front of you, you should change that delta into d. So it's a dv over dr. Go ahead and write it down first. dv dr. I explain later on why dv dr is better than delta v and delta r. Now, dv dr means you're differentiating the v. With respect to r, you will get your g, correct?
Mm-hmm.
So the gradient of the v is the same as the small g, correct? The gradient of the v is the small g. Correct?
Mm-hmm.
That's what this thing that you highlighted meant, the potential gradient, the gradient of the potential, dVdr, is gonna be the small g gravitational field strength. That's all. That's all he's saying. You might not know why that is true. I haven't explained why that is true, but at least I showed you already. He also didn't explain why. He also didn't explain why. He just say that this is correct. With the negative sign, which I haven't explained also. I'm pretending that it doesn't exist for now.
Okay. So there should be like a negative sign here.
So we still want to understand the negative sign sooner or later. We still also, if possible, want to understand why is this true, but this slide is not saying more than what I'm saying. It's just saying that for now.
Mm.
He even used the word relationship, right? Relationship between small g and potential. That's the relationship.
Okay.
Why is this important? In the questions lah, when we apply things lah.
Right.
For now, it's not the best answer, but for now, if you want to move on.
Yeah, those are all the questions I've highlighted. So.
I would probably say that you are ready to attempt some questions lah. I don't think you can answer them, but I think you can at least understand and roughly follow. Okay.
Thank you.
So you don't have the brilliant papers or anything like that, right? In Access lah, the soft copies lah. No, right?
Yeah.
Okay.
I
So
can ask
now,
my seniors actually.
that would be better. That would be better. I would rather you ask your schools than using other local school. Right? I would rather that, right?
I will ask.
Yeah, you ask now first, and I'm going to share you something in case that is not available. So, yeah. Would you kindly tell me or send me your email so I can share with you a Google Drive? Maybe WhatsApp me or something.
Yeah. Okay. There it is.
Have you sent me your? Oh yeah. Daniel Lam Chu. And I share with you a rather simple folder. The title is JC Physics. If you go to your Google Drive, you will be able to see that under share.
Let me just take a look. JC Physics.
Yeah. So what you want to see is not the JC1 Physics promo, because I don't think they have this topic. Definition list also not important. It's the physics topical question and answer, right? Okay, it's rather big, but if you download and open it, one of them will be the field questions. So nicely lined up in a topical way.
Okay. Wow, that's a massive file.
It is, it is, it is. Right. So maybe you just download it once and then it might be helpful for you. Okay, so once you do that, yeah, it ends up being a massive file, but there is electric field and gravitational field, right?
So I'll go
So
to the questions and
yeah, the questions. Is there an outline? Unfortunately, there is no outline. So this massive file requires a lot of scrolling. A bit annoying. A bit annoying, right?
just search for the things, right?
You can. Oh yeah, you can. Yes.
What am I looking for?
Search field. Search field.
823.
Gravitational field. Yeah. So we'll start with gravitational field. Most of the questions are gravitational field. Right? Okay. So I warn you that the moment they enter the gravitational field, they will assume that you can use circular motion. That is part of
Oops.
it.
Okay.
So that's why I say when you start jumping into the question, we'll see it as a bonus that you will have to take care of your circular motion. You will have to do it. So take it as a bonus. Now, yeah, to me, it's very simple. You see that the questions are very long one. You just see the length of the question is usually eight marks and above, something like that.
Yeah.
Okay.
So
breaking down to 1, 2, 1, 2 marks, right? Okay. So my first homework to you, just try to do 3 questions. Just try to do
3.
Right?
Okay.
Yeah. Just experience what the questions are. If you can even make some sense of the question, that's already good at this stage. Remember, your school haven't covered it. And your school is known for going very fast. So you're faster than your unreasonable speed of your school. Right? And that's why we take it slow, because you're already fast enough. You're already starting things early. You have the answer. So after you try the question, most probably cannot do this, cannot do what. You look at the answer. That is where your next questions will come. So you're going to ask questions of what the heck does the question mean? Right? This part I don't understand, this part I don't understand. I read the answer key, some I understand, some I don't. What does this mean? What does that mean? Okay.
I'll just do the first 3 questions.
That's up to you. That's totally up to you. Right. I put no limitation for it. So just like that. So I'm expecting more questions from you. Notice that I don't expect you to be able to answer everything. That's clear. But whenever you ask questions, good ones, and whenever it gets answered, at least you feel that you are learning something for now, for this one. So we continue on that. Are you okay with today?
Yeah.
So, are we sticking to the per week 2 times?
Yeah, that looks for me.
All right. So let's give it a try. You can do this until the next 2 weeks, right? That's the most.
Yeah. Wait, let me just double check. I can do it this week and next week.
This week, no, this week is done already. This week is already.
Yeah, so I can do next week. After next week, I'll be overseas until the 11th. Yeah, 11th.
Okay.
Not a lot of time. Yeah.
That is not a lot of time. No, that's not a lot of time. Even
I'll
for
be back in Singapore on the 22nd. I can fit in something in the afternoon if you want.
Rather than that, why don't you increase maybe next week to 3 times? Maybe.
Oh, okay.
Is that possible?
Yeah, I think it should be possible.
Right. Okay. So I'll see you next Monday. Wow.
Yeah, let me just mute for a second.
Yeah.
I'll be back in a few seconds.
Sure.
Does this weekend work for you then? If you want to do 3 times.
So Friday and Saturday I cannot one.
Sunday
So-
at night I can.
So why don't we try that on Sunday, Monday, and Wednesday like that? Something like that.
Let me see. Wednesday will have to be night time.
Yeah, I mean nighttime. Because the original schedule was nighttime.
Mm,
Correct.
yeah. Yeah, Monday also night time. Okay. Sunday, Monday. Okay.
Right. So what's our progress today? Our progress feels like it feels like you have graduated from your lecture note and now you're trying to attempt questions. But your lecture note only until G field. Obviously, we haven't covered the E field one. They are surprisingly similar.
That's good to hear.
So it is like you're already doing something more qualitatively than what you will do during school time, which is to go through the lecture note. That's all. Which after I hear that, obviously you're getting almost 50%. I think it's due to your tuition one. Cannot be due to your school class already. Cannot be.
Yeah.
Right. So your tuition must have had some effect, which is good to hear.
Of course.
Right. Okay. All right. Okay. You have your homework.
Sorry. Sunday what time?
If it is possible, we just go for the night time.
So
No
8
need,
10
no need so late, but maybe like
8 to 9:30 or 7:30.
7:30 probably okay. 7:30.
7:30 works here.
Okay, 7:30 to 9. We'll try that. Right. If there is nothing else, glad to have you today, and I will see you on Sunday.
Yes, sir. Okay.
All right.
See you. Thank you.
See you. Bye.